And then like at one point he'll be like, "Oh, we're live," like, pretending like it's very casual and he had no idea.
Welcome to part 2 of a walkthrough of Reverse Engineering Modular Edition. I am again joined with Jess, one of my collaborators and one of the co-authors on the paper. This is a reasonably self-contained second part of our 2-part walkthrough. In the first part, we trained the Modular Edition model and got to look at the graph and saw that it grokked. If you have no idea what I'm talking about, you should go watch the first video. But if you just want to see how to reverse engineer it, then you've come to the right place. At a high level, the goal of this video is to just try to convey the core bits of evidence and intuition for why we can actually understand this model and what really deeply understanding a model looks like. And hopefully along the way, convey some of the intuitions and parts of the research story for how we actually got here. To begin with, if you want to reverse engineer something, you need to really have a clear picture of what it is on a mathematical level. Like, what are the matrices? What is the computation being done? How does it all fit together? This is a tiny one-layer transformer. I am not going to try to explain what a transformer is, though I will link to a Mechanistic Interpretability glossary I wrote, which includes my attempts to actually do that. But I'm going to briefly review what's weird about this setup. The setup here is that we have 3 tokens: A, the first number; B, the second number; equal sign, the third token. It's a one-layer model. First, we've got the embedding, then we've got the attention, then we've got the MLP, then we've got the unembed. So what's going on internally? The embedding is just like a lookup table. We map each of A, B, and equal sign to some kind of vector. So just like, this is a lookup table. I apologize for my exceptionally bad handwriting. Now we've got the attention layer. This moves stuff from these 2 tokens to the equal sign. Some boring technical stuff that I'm not really going to go into is that it turns out the model doesn't actually need to use a lot of the infrastructure that being a transformer gives it, and there's various parts of the transformer that you can just round off to 0. In particular, we only care about the information of the equal sign position, because it's one layer. Things only get moved by the attention. There's only one attention layer, and the model just doesn't actually ever care about moving things from the equal sign to itself. So what's basically going on is you've got one attention head. It learns an attention pattern by getting a query from the equal sign, a key from each of A and B to produce just like a number on A and a number on B. Because it turns out that the attention from equal to itself is basically always 0, what you basically just get is like a number x on A and 1 minus x on B, because attention patterns add up to 1. There are 2 things. This is very straightforward. And then the attention moves information from A to the equal sign. We multiply by x, and then it moves information from B to the equal sign, and we multiply by 1 minus x. At this point, each of these lines is just like a lookup table. It's solely a function of A, it's solely a function of B. There are just 113 possible values, and they all map to a vector. And we've scaled by x, which is this like somewhat weird thing that turns out not to matter that much.
Is there anything interesting about the values of x? Which is to say, like, is x typically above a half? Is there any reason that the transformer is biased in a certain way?
X is like a half plus sine A minus sine B. This multiplication is like kind of scaling a bit by that. It turns out not to like actually be that core part of how the model does things. So I'm mostly just going to be like, observe, it's periodic, and then not actually talk about it again and only talk about the neurons.
Cool.
Writing on what the various matrices are along the way. This is the value. This is the output of the head. This is the key matrix. This is the query matrix. There's a bunch of skip connections around each of these layers. They also turn out to like not really matter, so we're going to ignore them. If we want to be rigorous, we could actually verify this by ablating them, but time is scarce. Go see the code accompanying the paper for more rigorous things. We now apply another linear map to get the neuron pre-activations. We then apply the relo activation of the MLP, which turns out to be where a lot of weird shit happens, as we'll get a little bit to later. Then we apply another linear map, W out, and then a final linear map, WU, or W unembed. Often people tie this and make it equal to the transpose of the embedding. I have no idea why. It seems wildly unprincipled, so I don't do that. And now we get the logits. The key thing to take away from staring at this diagram is that this is basically just a string of matrix multipliers with nothing in the middle. There's also positional embeddings, but they don't really matter that much, so I'm going to ignore them. Basically, the only things going on that aren't purely linear are these relos and this attention pattern multiplier over here. As it turns out, the attention pattern multipliers were less important than the relos, and we will dig into what the hell's going on later. So what is the main takeaway from staring at this diagram? The main thing I want someone to take away is that there just aren't that many matrices that matter. There's lots of parameters in here, but transformers are just very linear, especially when you observe some of the simplifications, it doesn't really attend from the equal sign to itself. And the skip connections around the MLP and around the attention don't matter that much. You can just ablate them. Though it turns out that it works better if you mean ablate them, that is, replace them with that average across all the data rather than zero ablate them. But that's kind of a tangent. The key thing I want someone to get from staring at this is just there are paths where you just have lots of linear products of things, and this means there are just not that many matrices we need to stare at. There's this chain, which is using the somewhat messy convention of matrices multiply on the right, because that's how my code is written. We have this entire path is represented by this matrix, because X is a scalar, we don't need to care about it. X is made via the matrix WE, WK, WQ transpose, WE transpose. This just entirely determines what the attention is. These two entirely determine what the neuron pre-activations are. And then this is W out, WU, and this just completely determines what the neuron to logits map is. The second thing I want people to get from staring at this is that because everything is so linear, there's just two bits of the network internally that could possibly matter to stare at. One of those is the attention patterns, X and 1 minus X. And one of those is the neuron activations in here. That when we're trying to interpret this model, we want to look at the few things that are the output of a nonlinearity, i.e., which aren't just part of a long string of matrices being multiplied together. And we want to focus on understanding those two things, and we want to focus on understanding these matrices.
Why is that? Why do we want to focus on the nonlinearity to drive the point home?
So the core reason I'm emphasizing this is that there's this fundamental result in linear algebra that the product of two matrices, if you do a linear map and then do another linear map, this whole thing is just a single linear map. And the way to think about neural networks is they're just these powerful engines of doing a fuck ton of linear algebra. They really, really want to do linear algebra, that they're really good at that. And we give them a tiny bit of freedom to not do linear algebra, because if you can only ever do linear algebra, all of your functions are linear, and this is kind of limited. But it turns out that with not that many nonlinearities, they're capable of doing really impressive shit. Some of the matrices are kind of factored, i.e., you can write them as the product of two things with no nonlinearity in between. But the product of these two things is a linear map. But it's kind of arbitrary how you can break it down. You could I don't know, double W out and halve W unembed. Or you could apply some rotation in the middle. W out, R inverse WU gives like the same product, but has a totally different thing in the middle. But like more deeply, the point is not you can't interpret this bit. It's that you don't need to. Networks are a mathematical object. You want to simplify them and find as few bits you need to understand as possible. And they're just like two interesting things in here.
I think that's a pretty good explanation. And maybe to give some sense for scale, could you talk about the sizes of these matrices, perhaps relative to each other?
Sure. So just going through and putting like dimensional numbers on things. Things are embedded in 113 dimensional space. The residual stream is dimension 128. Numbers kind of chosen arbitrarily. Technically, the input space has a special equal sign token, but this is kind of a special thing we can ignore and it's that worth thinking about. The internal head dimensions, like the value, the internal point along here, or the keys and queries, which are the things that go into the attention, are dimension 32. Here it's 128 again. There's 4 times as many neurons as there are residual stream dimensions. This is 512, 128, and then the output is 113 again, which means that this is 512 by 113. This is 113 by 512. And actually, I didn't explain this one particularly well. The thing on the right is not actually the embedding, because this position is always the equal sign token. It's just like always constant. And so you can just like get rid of this and just replace it with like final token query. And this is just like a vector. So this is just like a 113 dimensional vector. And so these are like not trivial matrices, but they're not that big. And it can do modular addition. Perfect. Just to round off the pontificating about maths and model architecture, one takeaway I want you to have from all of this is just, I did not need to actually look at the model for basically any of this, apart from some of my specific statements that like the model doesn't actually use some of the things it has access to, like the skip connections. All of this is just pure armchair analysis before I've looked at the weights at all. But this is already heavily simplified things. It's like, I care about what the neurons do and what the attention patterns do. There are just like some matrices I really want to calculate. Most don't really matter. This just like gives me a much stronger foothold and like a place to start looking. Maths tangent out of the way. The reason I went into that level of detail is just, I actually think this is one of the things you should do at the start of an investigation. Just make sure you like actually understand the moving parts of your model. Now that's done with. Let's think through how we'd go about interpreting the model. Before I jump to explaining the algorithm, I want to just try to walk through what are the kind of dumb things I could try just looking at this problem. The first is just going to be like, actually load the activations into the model. So I have this tensor called dataset that contains all of my data. I have this thing called labels that I believe contains all my labels. So now I first just want to like actually run my model. I'm going to use the transformer lens function, run with cache. This lets me just give an input to my model, and it will return the logits as it does normally, but also return this activation cache object, which just contains all of the activations and a bunch of other helpers, most of which aren't actually that relevant here, but some of them will be. One of the really nice things about this problem is that it's so tiny that we can just literally feed in the universe of all data that ever exists. Because there's only about 10,000 of them, and it's great. We just get like every logit. There's just 4 million numbers. You can just store everything in your GPU. It's wonderful. So you've got the activations. Now let's just get the like key weight matrices we might care about. These are going to be the nice factored multiplications that I mentioned earlier. For this, let's get the embedding. I'm going to get the what I'll call W neur, which is the weights from the embedding through the value weights of an attention head, through the output weights of the attention head, to the input weights of the neuron. I'm slightly cheating here in that these actually have a head index dimension, but conveniently everything will broadcast, so I don't need to think about it. And this code will basically just get me the input to neuron weights for each head. Then I want to get the weights from the MLPs to the output neurons. So this is the map from the relo activations out to the logits. And let's just do the same thing we did before. Because I train my model without layer norms or biases, we can just not think about any of that, and it's wonderful. There's also the attention weight matrices, but I'm just not going to focus on them for this investigation. Cool. So we have these weight matrices. The next standard thing to do is to just go and actually look at the activations and try to figure out what they're doing. The first thing I'd normally try looking at is just checking that the model can do the problem. So let's do that. Let's take our loss function, let's give it labels.
It is definitely important to make sure that you're trying to interpret something that's there.
My general philosophy of doing machine learning is you will shoot yourself in the foot. Being aware of this does not mean you will not shoot yourself in the foot. But it's often useful to try a little bit harder to check that all of your assumptions are actually true. I'm slightly cheating here because I did a bunch of this investigation, so I am kind of comfortable asserting some random things are true without checking them very hard. Now to look at activations, a pretty good first thing to do is just get all of the shapes. Yeah, a lot of activations. The concrete ones that I am mostly going to care about are the attention pattern, the neuron activations, and there are some various helper functions in the cache to let me call those the things that I want. Let's just try printing the average attention pattern. For this, I'll use the syntax name of activation, layer index, feed it into cache. I get the attention pattern out. And let's just average this across the first dimension and then plot it and see what happens. I should really label my axes.
And to throw in a quick comment to tie to part one, NPX, I believe, is the name of Neil Plotley, where Plotley Expressor usually goes by PX.
Yes. So I think that having great graphics software and the ability to plot things nice and exactly the way that you want is a really useful feature when doing research, and you want your feedback loops to be as tight as is humanly possible. Plotly is my favorite graphics library. You can do things like hover over it. If you hack at it right, you can get things like these incredible log axis toggle buttons, which took me far too much effort to figure out how to make. But also, generic Plotly does not do exactly what I want all of the time. And this makes me very sad. So to solve this, I wrote my own incredibly scrappy and hacky and terribly documented library that I'm currently calling Neil Plotley. I do not recommend anyone else uses this, but I will use it for this tutorial. And if you want to edit this tutorial, you can either try using it and seeing if things break, or go use a normal graphics library like a normal person.
And to reify that with the previous point, I think plots are a good way to check if you're shooting yourself in the foot actively. Things like plots and shape checks and looking at the first, some first values of a tensor can give you a sense for what's actually going on. And perhaps the subtle ways that you could be adding a lot of extra noise to your workflow and pain to your workflow.
Common misconception is people think that research looks like writing a lot of code. If you're doing interpretability research, this looks like writing some code, plotting your data, being confused, staring at it, writing more plots, and iterating until you might become less confused. As a illustration, so what I've just plotted here is average attention pattern per head. As I'm staring at this, I'm like, wait, what exactly am I looking at? What I'm looking at is for each head, this is just the average attention between each pair of positions. But as I pointed out earlier, I don't care what the model does about moving information to the first position or to the second position. I only care about it moving information to the equals position. So let's just get rid of the A and B parts. I happen to know that the shape of this array is batch, which I averaged over by head index, by destination, by source. So let's just make destination 0. And then let's redo this all. So now I've got this majestic graph where every row is an attention head, and we're looking at the average attention paid from the equals token to the previous two tokens. If you look at this graph, you may notice something interesting, which is that these are all basically a half, and this is basically 0, which is the claim I made earlier that the model just doesn't care about the equal sign. This is like a pretty sensible first thing to do, just like, what is the flow of information, what is going on? We see that the model is symmetric between A and B, which is not pretty surprising. A plus B is B plus A. A natural next question is, okay, so does the model just not use attention at all? Is it just always a half? This is easy to test because we can just like print this for a specific input. Let's just plot this for 0, 0. What happens? It actually does look pretty even. What about 5? Cool, that's not pretty even. This is the benefit of doing randomly chosen numbers rather than 0, because that sometimes leads to things being weird. So let's do something interesting. A really nice thing about this problem, because our batch is just all data, and all data is all pairs of numbers between 0 and 112. If we take any individual number in our network, we can plot a beautiful heat map of that number across the A dimension and across the B dimension. To demonstrate, let's take our cache and the pattern, and let's look at the attention for head 0 paid to the equal sign from the A token. That is head index, destination -1, source is 0. And let's just show this. Because this is a p-squared dimensional vector, we'll reshape it. General point, I'm going to do a lot of weird tensor manipulations. I have the shapes of these tensors fairly clear in my head. The important thing when watching this video is not to follow the details of all of the tensor manipulations. Oh my god, that is so pretty. What is that? Let me just add some labels. So a natural next thing to do is to take this graph, stare at it, and to be like, what? That is so periodic, what the hell is going on? One natural thing to do is to check this for other heads. So let's go do that. This is going to involve some more weird tensor manipulation, because I now no longer want index on the head dimension. For this, I'm going to use my probably all-time favorite tensor manipulating library called inops. Inops rearrange just lets you take a tensor with some shape and write down what that shape is using words, and then tell it a new shape to move it to using words. And it just works beautifully. The bracket notation means these two axes are flattened into the same axis. Can you unflatten them? A has length p, B has length p. Can you infer this? And it just does, and it's great. Let's move the head dimension first, so I can make that a facet dimension. And yeah, we stare at this, and we're like, what? What is going on? The next natural step is plotting neuron activations. So again, we can just pick any number in the model and say, just take this number for every pair of inputs plotted as a heat map. Let's just plot the first 5 neurons. It's worth explicitly saying that I'm deliberately focusing on activations that I expect to be interpretable. The jargon for this is they lie in a privileged basis, which in this case basically just means they're the output of a nonlinearity where each number in the output of the nonlinearity has some reason to be meaningful. Like, for the MLP layer, we do a ReLU on every single number individually, so each number is either on or off. This empirically means that often that number is directly interpretable in a way that some weird mix of numbers isn't. This is kind of a weird and subtle concept, and I will link to a long-ass mechanistic interpretability glossary I wrote that tries to give more exposition on that. The key thing I'm contrasting it with is, say, the vector in the residual stream, where because it's an intermediate state in some linear map, there's no real reason that any coordinate of that should be meaningful. So I just want to go and try to plot some neuron activations. Let me just look at the shape. I completely don't care about the 3-axis here. I only care about the MLPs on the final position. Actually, I think I'm going to go back and just define the helper variable, which are just the activations that I care about. Cool. So I've just defined the thing, which is the pattern to the A, the pattern to the B, the neuron activations, and the neuron pre-activations, i.e. post-ReLU and pre-ReLU. I basically assert that to understand the model, we just need to understand at least some of these things and how things fit between them. So we can take our neuron activations from earlier. Let's look at, say, the first 5 neurons. We use the magic tensor rotation code from before. Oh, crap. Great. And so when we stare at this, we're like, huh, that's also weirdly periodic. What is going on? These are kind of squashed, so it looks kind of weird, but it's a pretty symmetric pattern. Zooming out a bit, a good chunk of the initial research story was just doing dumb shit like this and staring at things and being like, what is going on? This is so periodic. There's clearly some legible structure here that can be understood. Credits to Tom Lieberman, another one of my co-authors, for doing a lot of the initial work here of just noticing things are weird and interesting. I want to talk a bit about a different kind of dumb thing you might do at the start. Here, the idea is neural networks are big. Neural networks have lots of dimensions, both in the weights and in the activations. There are lots of techniques to look at high-dimensional things and find a couple of meaningful directions and reduce them to lower-dimensional things. My personal favorite by far is this thing called singular value decomposition, which I'm not going to try to technically define right now, and it's not a big deal if you don't know what it means, but in brief, singular value decomposition takes an arbitrary matrix and decomposes that matrix into an orthogonal transformation V. We pick some set of vectors that are all orthogonal in length 1 and multiply a vector by those. We have a diagonal matrix S, so we scale each thing by like some constant number, and we multiply by another orthogonal map U to the output space. The key thing here is just you can take any matrix, you can do this thing, it's perfectly linear, and a really nice thing about S is that it's ordered. Big things come first, and it turns out that often only a couple of the numbers here matter, which means that only a couple of directions in V or U matter. Either way, the most important directions often can be kind of interpretable. This totally does not always work, but it should be in your toolkit of dumb things you try at the start of an investigation. So let's try it on the embedding matrix. The embedding matrix has shape vocab size by internal model dimension, 113 by 128. We kind of expect stuff over the 113 side to be more meaningful, because this is our input space that has lots of nice structure, while this is residual stream space that's kind of weird. So when we look at the singular values, we get this really weird graph, which drops off like extremely rapidly. For context, if we tried to do a control where we took a random Gaussian matrix with the same shape, There's this cute function, rand_n_like, for create a matrix that's this shape, but with random numbers in it. This kind of thing is just like a pretty good sanity check if you get results and they look weird, but you're not sure they're weird. So we look at this and it's like, okay, there's like 8 directions that matter, 2 that matter a little bit, and then most just like don't care. This is already interesting because the interpretation of this diagram is that when you embed something, the output is basically just a combination of the 10 vectors corresponding to these numbers. And most things just like completely don't matter. And this is really weird because the model has 128 dimensions to play with. So it's intentionally chosen to be like, most of these don't matter. But we were training it with heavy weights decay. So it's not incredibly surprising that we'd rather get rid of some dimensions. These are the principal components. We see that on the left, there's some structure. On the right, who knows? But as we saw here, things just don't matter from like 9 onwards. So let's zoom in. And we see this gorgeous periodic structure. The intended takeaway from all of this is just, here is a lot of kind of naive things you might do if you're taking a problem and staring at it, and you have no idea what's going on. And they give us a lot of clues. We don't know what's going on, but we can stare at the mathematical structure and figure out the sensible things to look at. We can visualize these, and we can try to do dimensionality reduction on the weights. And we've learned cool things. This doesn't always work, but sometimes it does. I'm not going to go into it in the interest of time, but another technique that I'd often do when I'm getting started on a problem is to pick some concrete inputs and then try to understand how the model does these inputs. Like, are there parts of the model that are unusually responsible? Generally, models will kind of specialize and have some parameters that are useful for some things and not for other things. This turns out to completely not work in this problem for reasons we'll see later.
So one thing this previous section on analysis made me think of, you showed some graphs, right? And they were periodic. One cool way that that rhymes with the problem is that the problem of modular addition is by definition periodic. And it reminded me a lot of the early interpretability work, the earliest that I know about anyway, of like word to vec, which are these word embeddings from like 2013, I think. They showed that like the vector representing king, if you subtract the vector representing man from that, you get the vector representing queen or something really, really close to it.
King minus man equals queen minus woman.
Yes, right. It's king minus man plus woman equals queen.
Yes.
Which is the same thing as what you said. Thank you. The high level, I guess, similarity is like deeply thinking about the structure of the problem and the problem space that you find yourself in as a guiding light for what types of graphs and relationships should pique your interest.
Yeah. So the way I think about this is it's often really helpful to have some good domain knowledge of what is the problem your model is trying to solve, what kind of structure exists in the problem that could be exploited, and what kind of things might the model be trying to do. My main day job is reverse engineering language models. I'm not a linguist. It'd probably help if I was. I personally find it easier to reverse engineer how the model does things like Python code, where I actually understand the structure, than language with lots of weird grammatical things. But fortunately, I do have a pure maths degree, which it turns out is occasionally useful for something. Modular addition turns out to be a surprisingly rich thing to think about. So my naive thing coming into this problem was modular addition, basically addition. The way I would do addition if I was a model is probably something like how it's implemented in computers. You have some arithmetic logic unit, which has a bunch of ones and zeros. It represents the numbers as binary. It does some basic routines on that, and it adds everything together. But it turns out that this is like a very discrete way of thinking about it. And models are continuous things that are a big soup of linear algebra. They want to find a way of representing things that's like geometric or at least linear, which involves linear transformations. Modular addition is actually like a surprisingly pretty mathematical object because Modular addition is composition in the group of Zn, integers mod n. This is totally a math tangent. You do not need to understand this. But it's very cute for the 3 people in the audience who did a pure maths degree. Modular addition is the cyclic group of n elements. Lots of things are equivalent to the cyclic group. There's so much rich theory about groups, and one particularly cute area is representation theory, which is about how you can understand a group as actually thinking of each element as a linear map on some space. It turns out that the representations of the cyclic group on n elements are just rotations around the unit circle. Another way of phrasing all this without thinking about representation theory is you can just take the geometric transformation, take a point in 2D, rotate by 1/nth of a full rotation. Figuring out a plus b is finding the rotate by a over n operation, the rotate by b over n operation, and composing them. We have this gorgeous diagram that Lawrence Chan made, basically demonstrating the algorithm the model has learned. The key idea behind all of this is the model has decided, screw your framing of modular addition. From its perspective, anything equivalent to the cyclic group is the right way to think about it. And it said, okay, I'm going to think about these as linear transformations because linear transformations are easy. It's learned to convert the 2 inputs, A and B, into sine and cosine waves, which represent the geometric transformations rotate by A times some angle W and rotate by B times some angle W. This is a thing which is often confusing to people when they first look at it. So I'm going to take a moment to try to really digest what this means. The model wants to think about the inputs as being linear transformations of space. But most of the model's ability to look at linear transformations comes from its parameters, which are learned fixed things that are not a function of the input. Here, it wants the linear transformation that is a function of the input. And so it learns this weird form of sine and cos, because if you actually look at the geometry of it, the matrix of the rotation rotates by A times some angle W is you define some W that's a multiple of 2 pi over n, some number of 1/nth of a full term, and then your matrix is cos WA on the diagonal, sine WA, and minus sine WA. All of this is just random maths facts that are not at all novel or particularly complicated. The key thing is that if the model wants to internally represent the geometric transformation rotate by A, all it needs are these 2 numbers, and it can represent each of these as some direction in residual stream space. The second important thing to note is that when people look at this, they're oh my god, it's learned the sine function. Sine's complicated. Sine looks like this. How has the model learned that entire thing? That's so impressive. And this is wildly overestimating how competent the model is. What's going on is that the model only ever sees the inputs that are the numbers from 0 to 112. So it only needs to know what sine is for these inputs, which means that rather than needing to know this full elaborate thing, all it needs to do is know what this is, and what this is, and what this is, and what this is. You can just memorize this. This is just vastly easier than memorizing an actual complicated function. You can just learn a lookup table, and the embedding of a transformer is just literally a lookup table. There's some fixed vocabulary of tokens, and for each token, the model just separately learns some vector and stores that. That's just how it does sine and cosine, and we'll later go and see that this is happening. Then weird shit happens here, where the model says, okay, I've learned rotate by A and rotate by B. I want to look at the composition rotate by A and rotate by b, and do both in succession. This is the rotation of a plus b. So just as we had here, the two numbers we need to represent to do this are cos w a plus b and sine w a plus b. By trig identities, these are linear combinations of these terms, but where we need to take products of things. Also, there's a typo here that we should really fix. This should be a B, not an A.
Who knew you would need to interpret the interpretability graphs?
Who knew? Clearly, you don't need to submit a perfect paper. Anyway, so the model is now doing a rotate by A, then rotate by B, and figure out the composition. And in order to do this, it basically needs to take these features it's learned, these four numbers that correspond to different directions. It needs to multiply pairs of them together, and then add or subtract these multiplied pairs. An important thing to note is that it's multiplying together two inputs, two activations. It's not multiplying together an activation and a parameter, which is super easy. And how it does this is going to turn out to be most of the meat of understanding this. While adding and subtracting them is super easy, because that's just a linear operation on activations, which is just a matrix multiply. And as I've hopefully established by now, models are really fucking good at matrix multiplies. Now we get the final bit, which is where things get a bit weirder. So the model, by composing these two rotations, has got something that is purely a function of a plus b. And at that point, you've kind of basically won. Because it's around a circle, we get mod n. So here, this is a plus b rotations, but we go a little bit more of the way around the circle, so we can just kind of ignore that, so we get the mod n for free. But we need to output the logit c that is equal to a plus b. This happens via the kind of weird procedure. So the MLP neurons represent these terms as some directions. We then apply the linear map w out, w on embed, or w logit, as I described earlier, to get now a logit for every token C in the output, and then we do a log softmax over that. We want the output probability for the correct token to be way higher than the rest, which basically means we need the logit for the correct token to be way higher than the rest. This basically means we need to learn a linear map of these terms, or of this rotation, that is biggest for the correct answer than of any of the incorrect answers. Turns out that the way to do this is by rotating backwards by C, composing that with the thing we had here to get a rotation by a plus b minus c, and then checking, is this the identity? Does this keep me in the same place? Turns out that it just does. If you can project onto the axis so that you get the bit that is 1 when you've got the 0 rotation, this is biggest when C is the correct answer, and if it's the biggest when it goes into the softmax, it's the biggest when it comes out. As we'll see later, the models have some tricks to make it really, really big rather than just a little bit bigger than the rest. Composing a plus b with backwards C is just another linear operation. This time, C is a learned thing in the model. It's a parameter because you've got separate parameters for each output logits. So rather than this being a complicated non-linear combination of inputs, this is just a matrix multiply with an activation and everything is happy and good. That was a long, convoluted explanation. So let's recap through the key points. Modular addition can be thought of as rotation around the unit circle. Addition means do one rotation, then do the next rotation. And we get mod because if you wrap around the circle, you're back to where you started, which is the same as not rotating at all. The model learns a lookup table to convert the inputs to sine and cosine of some angle w times a, where w is the unit angle you rotate by. For now, let's just say w equals 2 pi over n for simplicity. Mathematically, it's pretty easy to compose these two geometric operations to get a plus b. Internally, the model implements this with these triggered entities. The model then applies minus C, i.e., it's trying to learn an output logit for each output token C. The way it does that is the output logit. We compose A and B to get the A plus B rotation. We compose with the backward C to get an A plus B minus C rotation. And then we project onto the y-axis. When C equals A plus B, we get to the top. Otherwise, we are not at the top. So we've learned an algorithm that makes the logit for the correct answer biggest. And this is basically a solution to the problem. At first glance, people often get confused about what is easy and what is hard in here. The key thing is that this is actually really easy because we're not learning sine and cosine in general. We're just learning a lookup table on the inputs. Multiplication is actually really hard. This is mostly done by the relo activations and a little bit by the multiplication of the attention pattern with the token embeddings. Adding and subtracting these is really easy. That's just a linear map, which models are really good at. And composing with C is really easy because C is not an input, so you can do this with learned parameters, and this is just a linear map. Now let's go and stare at the model and try to show that all of this is happening. This is going to be in roughly 3 parts, showing that sine and cosine are learned at the start, showing that the model learns to multiply things, and showing that it learns to compute the logits correctly according to this formula. So that was explaining the algorithm. The first thing I want to do now is analyze the embedding and show that it's a lookup table. A key observation is this result we had up here, that the principal components of the embedding, i.e. the directions across the input that seem most meaningful, are like really periodic. If we plot them, things look even cleaner. So we get this graph, which is kind of a mess. But if we look at any particular one, it's like kind of periodic. It turns out it's actually very periodic, but it's a high frequency wave that's highly discretized. So let's think about how we can show this. The key result here is that if we have a vector corresponding to sine of A times some angle that's a multiple of 2 pi over n, and we have any other vector that's sine in some other frequency or cos in any frequency, these vectors are orthogonal. Let me just write some code to generate those. I'm going to call this the Fourier basis. So I'm going to start with the constant vector, and now I'm going to iterate through every frequency. I only need to go from frequency 1 up to p over 2, because beyond that, things are symmetric. Okay, so I just wrote a bunch of kind of convoluted code. Here, I made this thing I call Fourier basis, which is a massive stack of sine and cosine waves of different frequencies, where the key thing is that the frequency or the angle is some multiple of 2 pi over n. If you look at the algorithm over here, it doesn't actually matter whether, say, the rotation corresponding to 1 is like 2 pi over n, 4 pi over n, 20 pi over n. The bigger it is, the more times the thing will wrap around. But it still is the case that when you do that n times, you end up back where you started. You just might wrap around a bunch of times in the middle. But for the purposes of the model, this just doesn't matter. And because we're doing a prime, it actually just has zero reason to care which one we're using, because random maths fact is that if you multiply every number mod a prime by some integer, the numbers just get shuffled, and the model doesn't actually care about the ordering. And so here we just have like a bunch of waves of different frequencies. Like 1, it's got 1 nice thing. Sine 4, it's got like 4. And just to reiterate what I was saying earlier about discretization, if you look at Adno components 25 to 29, you end up with this, which is like incredibly discretized. And this hopefully makes the point I made earlier. The model does not need to learn silence in pure sense. The model just needs to learn like the kind of lookup table of the discrete points on the curve. And the key fact about the Fourier basis, that's the reason I went on this tangent, is that every part of the Fourier basis is orthogonal. Every vector in here is orthogonal to every other vector, and I scaled it so that things were all unit norm. So if we do this, we should get a matrix which is just ones on the diagonal and zeros everywhere else. My VS Code gets sad when I have too many graphs. I really need to try fixing that bug. So let's clear all cell outputs. Now we can use this to analyze the embedding. And the key idea here is that if we think that the embedding has some direction, and that this direction corresponds to sine WA, then if we multiply the embedding with every vector in this Fourier basis, then the sine WA direction is going to get 1, and everything else is going to get 0. And another way to put this is that if we multiply the embedding by the Fourier basis, we will get a bunch of directions in residual stream space that correspond to the different functions sine and cosine in different frequencies. This is not a statement about this model. This is just like a mathematical statement about any 113 by 128 dimensional matrix. So now we can use this to try to understand what's going on in the embedding. We're treating the embedding as a linear map from the 113 dimensional space of inputs to the 128 dimensional residual stream space. Normally, we just think of this as a lookup table because you just feed in the vector that's like a 1 in the A position, 0 everywhere else. This just gets the output vector corresponding to that. It turns out that you can think of this as just we imposed some basis on the input space, and that basis was first basis vector input 0, second basis vector input 1, etc. But we could instead use whatever basis we want. And it turns out that if we do the Fourier basis, the set of directions on the input space that's like sine and cosine waves, we get this, which is clearly interesting and meaningful. For contrast, let's look at it without that. And it is kind of a mess. Something here is clearly exciting. What's going on? We can add in some axis titles. What we see is that the lines corresponding to like a couple of angles are big. Frequency 17, frequency 25, frequency 32, and frequency 47 are big. Everything else is small. And there's this like really faint one, 50. So what's going on is that the model has decided, I want to learn this lookup table. It wants to have meaningful directions that correspond to these angles. And further, the model only cares about 4 angles. We can make this a bit cleaner by just taking the norm across the residual stream dimension, because all we care about is like which inputs are big versus small, rather than what the actual values are. And when we do this, we see, 17 big, 25 big, 32 big, 47 big, this one like a little bit big. Most basically don't matter. Just a final verification that these are actually the thing the model is trying to learn. So each of these rows is like a direction in the residual stream. And if you want to recover some direction, you want to make sure that it's orthogonal. We can just check that these directions are actually orthogonal. I'm just going to hand code what the right things are. So I've just like hand coded what these frequencies and entities are. Let's define the Fourier embedding because we might want to refer to this in the future. And let's just take the residual stream vectors corresponding to these 8 key frequency terms. And let's just plot the relative dot products. And yeah, we see that things were orthogonal. The model has deliberately put these in a way that it can recover things later on if it wants to. This isn't actually that strong a result. Most 128-dimensional vectors are orthogonal with each other, but it's like a good sanity check. I now feel pretty convinced that the model has learned to embed things as a lookup table, giving it sine and cosine of a couple of frequencies. An actual question is like, wait, why does it have 4 frequencies? What is special about these numbers? 17, 25, 32, and 47. What's going on? So one thing that I haven't really explained is we got this W. And I was like, W doesn't matter. But the model has learned 4 Ws. 17, 25, 32, and 47. And I think a very reasonable reaction is to be like, what? Why do these numbers matter? Why do other numbers not matter? Also, thank you to Jess for prompting me to think about graphic design and making everything bigger and making my legend titles larger. Which hopefully the 5 of you who have, for some masochistic reason, decided to watch this on your phone will appreciate. So the first thing to note is that every frequency is kind of equivalent to the others. As I briefly mentioned earlier, when you multiply by any number mod p, you just shuffle the inputs and shuffle the outputs in the same way. From the model's perspective, this is exactly the same, so it doesn't care. So the fact that it's like 17 and 1 doesn't show up is totally meaningless. The next question is, this algorithm seemed great. Biggest logit, C equals A plus B, you need a single W. Isn't that kind of weird and wasteful to learn 4? And so the key idea there is this idea of constructive interference. Let's draw a plot of cos of 17 on the side. And we see that it is biggest at 0, but it's not way bigger than everything else at 0. This is actually incredibly close. It's like 0.0002 apart. If we do this for, let's say, 50, which is another co-frequency, we get a similar thing. Let's plot these on the same graph. So if we look at this horrifying graph, what we notice is that all of these are really big at 0. It's like the biggest, cos 1, what we expect. It's 0.133 because I made everything unit norm, which meant I scaled them all down. And there's like often peaks at like pretty high values, but they aren't the same high values. We can see this because if we take the average of this, we get what's called constructive interference. Basically, all of the waves reinforce at this big central peak and get smaller everywhere else. This actually got suppressed less than I expected, but it's still like, we've gone from 0.0002 apart to 0.3 apart. It's like a pretty big difference. Probably we could get the difference higher if we had like better coefficients on them rather than just averaging, but like the key thing here is it's useful to have more frequencies. The final question is, why these 4 frequencies rather than any others? To which my answer is, I don't know, my guess is it's kind of random. When I change the random seed, I get different frequencies and different numbers. Maybe it's choosing ones that don't all kind of be about as high at the same point, but the model just wants a bunch of things to get constructive interference. So model has learned a lookup table, and we learned a lot of fun things about the Fourier basis along the way. Now we're going to look at the embeddings. So just to remind ourselves of our pretty activation graphs from earlier, we plotted the first 5 neurons, and we got a pretty thing like this. We have neuron activations, they're all periodic. And this algorithm predicts that the neurons are going to have significant components in the directions of sine W A plus B and cos W A plus B. The first way that you can think about these is use this technique called a 2D discrete Fourier transform, where what we're basically doing is we're taking this periodic heat map. Let's just plot this for just the 0th neuron. The key idea is that this whole thing is a 2D periodic-ish function. And that anytime we take a wave over the A dimension and a wave over the B dimension, and take the element-wise product of the two, then we get a periodic-ish 2D function. This one is cos 47a, element-wise product of cos 47b. And if we stare at them, these kind of have the same period-ish. They look vaguely visually similar. It turns out that you can take any function, any 2D heat map like this, and break it down into a sum of pairwise products of any periodic function over A times any periodic function over B. There are P of these, and so P squared possible pairs. And from a linear algebra perspective, all I'm saying is there is a basis of periodic functions over the space of P by P 2D images, and we can convert things to that. This plot is what happens when we do that, and we get this incredibly sparse thing. The way to interpret this is that this neuron is the sum of a bunch of terms that look like this, where this is the coefficient of cos 47a times cos 47b. This is the coefficient of sine 47a, cos 47b, etc. These are the coefficients of the terms for constant a times cos 47b. There's this annoying thing where Plotly does not change its hover labels, despite me changing the axis labels. X means B, Y means A. If we plot these, we can see that they are like kind of periodic, but in a pretty different way, where it's now this kind of like funky 1D periodicity, as you'd expect, because they're constant. So what this is saying is that we can compute this neuron heat map as a linear combination of heat maps like this and heat maps like this, and there's only like 9 terms that matter. That's what I want your main takeaway to be from that whole thing. You can take any function on any 2D heat map like this, so essentially any scalar function on the two inputs A and B. You can break it down into some linear combination of 2D periodic things like this. Most things will just be some like total garbage when I do that. Like if I take this and I replace this with like torch rand n, like the trick I did earlier, it's gonna look like total garbage. Let's call this random so it stands out. This is what looks for a random thing. It's total garbage. But this looks incredibly sparse. And because it's sparse, this means we can get a lot of traction on understanding it. And it tells us that the model is like deliberately making this neuron represent these terms involving period 47. If we refer back to this term, sine times cos, appears here. This one, this term, cos times sine, appears here, and etc. So because these both correspond to directions in the neuron's output, we can get out these terms. So this is just one neuron. You can't infer 2 numbers from a single neuron that involves 9 terms. But it turns out that if we put like a bunch of other neurons in here, we get pretty similar looking things. We can do this more generally, where, oh, this is even sparser. It like scarcely has a cos term. So that was just some like high-level exploration. Now we can get some neuron clusters. I decided to cut the last 5 minutes of coding because it was just really boring implementation details. But you should go stare at the code in the notebook if you want to follow this in detail. Very roughly, what I did is I said, okay, let's just take each neuron. Let's look at the 9 elements corresponding to the terms of a frequency. Let's look at what total fraction of the variance of that neuron they explain. Fraction of variance here just means like you take the sum of squared elements of the neuron, you take the sum of the squared elements in those 8 or 9 cells, and then you take the ratio. You do that for each frequency. And I also made the mean of each neuron 0 because I don't care about the mean. The mean doesn't depend on the inputs. And here is the majestic graph I get when I do that. Why is everything off by 1? Sorry, I had another bug which I just went and corrected. Here is now the correct diagram. What this diagram shows me is that for each neuron, there are bands corresponding to the key frequencies, and lots of neurons are just really, really well explained by one frequency. Like, this is 0.85. That means that of the 12,000 elements of the grids we had above, those 8 explain 85% of the total stuff the neuron has. And a experiment, which I can't bother to do right now, is that if you ablate everything that's not captured by this, model performance is basically fine and sometimes slightly improves. One thing to check is this like what all neurons are doing, or just some weird thing where there's just like some things that are like really salient? Cool. So what I just did is I took the plot I had above, and then I took the maximum frac explained across all the frequencies per neuron, sorted them, and have plotted it here. Notes that this is not the like index of the 29th neuron I just sorted. All we see is there's like a decent chunk of neurons that are like explained-ish by this, like, I don't know, 30% up to 70% for the first like 90. But then beyond that point, like the remaining 400 neurons are just very well approximated by this. I'm gonna leave these neurons for now and try to get the final step of this algorithm. So we know that the neurons have a bunch of terms in their output corresponding to this, and a constant. But I'm specifically claiming that the output logits look like this. Cos W A plus B minus C, which is this linear combination of these, which correspond to particular directions in neuron space. Let's try to figure out how we can extract these. So now I'm going to try to interpret the neuron-logit weights in the same way that I did the embedding. Recall W-logit is the MLP output weights. So we have this neuron to output logit matrix, and we predict that it's going to have vectors corresponding to cos C and sin C for each output logit C, for each key frequency W, and that each of these is going to extract out this cos W A plus B and sin W A plus B term from the neurons. And we can just verify this. First, we want to check that it, like the embedding, is kind of sparse in the Fourier basis. This basically looks the same as before. So yeah, we see there's some like random crap, but for the most part, it is these frequencies. So another prediction this would make is that for the neurons that represent a specific frequency W, we should only see cos W and sin W. for that frequency, we shouldn't see it for the other frequencies. Like, these should be clustered. And it turns out that if we take this neuron frequency norm and we're like, I don't know, let's take the neurons, let's take like neurons 17. So like the ones such that this for that neuron is like over 0.7, say. This is going to give us a Boolean mask of which neurons seem to really like frequency 17. And we can put this into the thing we had above and verify that when we restrict to just these neurons, let's just sanity check that the total number of things in there is sensible. Yeah, it's like 100 neurons where it's true. Cool. For this, we see, it's like not perfect, but it definitely strongly skews in this basis. Maybe let's like up the threshold a bit, because there's probably just some weird neurons that don't quite fit that. No, that totally didn't work. But there's something over here. Maybe this network that I've trained for the purpose of this tutorial is slightly different from the one that I interpreted in the paper. That sure would be embarrassing. So we think these correspond to the cos C and sin C that we had over here. To demonstrate this, let's just take the direction in neuron space that corresponds to the sin 17 term, and let's see what that corresponds to in neuron space. So let's study sin 17 as a specific key frequency, and we're going to take the W-logits in the Fourier basis, and we're going to take the component in the sin 17 direction. So we take this as a vector over the neurons, and we see that it's like pretty spiky. So we've seen that W-logit corresponds to a direction in neuron space. Let's figure out what this direction actually corresponds to. Let's just take the vector of neural acts. So this is a p squared by 512 tensor. And so if we dot product it with the direction in neuron space that maps to the sin 17C logit direction, we're going to get a vector over the inputs corresponding to sin 17C. And when we do that, we can now just plot this. Let's plot this in the Fourier basis. I should really have written an actual function to do this, but whatever. Writing functions totally breaks my flow when I'm doing a tutorial and not trying to think about writing elegant, maintainable code that other people can read and understand, because why would I care about that? So what even is this? Fourier heat map over inputs for sin 17C. And let's... So I mean, this is like less compelling than I hoped. Probably good to just spend some time screwing around when not filming and try to figure out what the hell's going on.
That's how you know that VS Code didn't sponsor this video. We're not bought out. Like all the other mechanistic interpretability tutorials, straight to the people.
We have our autonomy and independence. Though if you're looking to sponsor us, hit me up.